Welcome to the pre-recording of lecture 17 of MCS 481. So our previous lecture was spent on the midterm. So in this lecture we start the second half of the 10 chapters in the textbook, the 10 chapters which we will carefully cover. We start with the problem of point location. And to solve this problem with a data structure, we will introduce trapezoidal maps. So what's the problem? Well, you must have had this problem also. You are in a foreign city and you walk out of your hotel, and after a couple of blocks, you are lost. If you have a map, then the first important problem is, do you know on the map where you really are? So fortunately, smartphones may actually help you with this. And what we will cover in this lecture and also in this entire chapter is how we can solve this problem. So we have a map. It's a planar subdivision. We look at the edges. So you can think of this drawing here as a road map. The edges are roads. The vertices are the intersections between the roads. And the space that between the roads and the vertices, these are called the faces. So there are three cases for your query point. Either you can be inside a face, think about an open space, a square or a plane. You can be on the road, the second case, you are on the edge, or you can be on the intersection point, then you are on a vertex. So these are the three possible cases in the planar point location problem. So this is the mathematical formulation of given a map, and here I demonstrated, or I referred to the analogy of a city plan, but it could also be in open nature you could have canals, or the edges could be line segments representing rivers, and you want to determine, given the map, given coordinates, you could have longitude and latitude, determine where you are. So this is the point location problem. Very practical for geographical problems. And also we are somehow in the area of geographical information systems. So we are going to solve this with a data structure. So here is the same subdivision as on the previous slide, but we are going to partition it in slabs. So what we are going to do is, for every coordinate, we're going to, for every point, we sort the points on the x coordinates, and we run through the list, and we are with every sorted, so when we sorted the x coordinates, so with every sequence, so we have a sequence of numbers, and the numbers in that list are actually indicating the vertical lines through the vertices. So we just have sorted, what we do have a sorted array of numbers. What we visualize is that every number represents a vertical line, and between the vertical lines we have a slab. So I pictured one slab here, taken out of this partitioned subdivision. So what do we have is that the edges in the slab are actually sorted as well. So they are sorted from top to bottom, and every region in the slab belongs to a unique face. So in the slab we can look at where the edges are, and we can check in between the edges to which face that region belongs. Why does that solve our problem? Well, look at the queries now. So we have a partitioned subdivision. So I should say that the properties, it's properly a partition. So in the three cases here, we see that in the first case, when the query point belongs to a face, we are in this lower region of this next to last slab. In the first slab, we have our second query point on the edge. And then our third case, when it is a vertex, then actually you could say that it is on the vertical intersection, and you can actually immediately go to the vertex. So it's on that vertical line. Okay, when you have a query point, you have two coordinates, x and y, or longitude and latitude. We first look at the x coordinate to locate the slab. So we have the slabs represented by the sorted array of x coordinates. So sorted arrays you could also see as a collection of intervals. So we locate the slab, and then within that slab, everything is also sorted from top to bottom or bottom to top, and we will find then which region or which vertex, which edge, the query point belongs to. Okay, so what is now the cost of this query algorithm? Well, locating the slab can be done via binary search, and that is logarithmic in the number of vertices. We could also run a binary search on the segments that are in the slab. So in some sense, we have covered the the line segment intersection problem. So we can actually order the segments in the slab also from bottom to top or from top to bottom. So there are two binary searches. So in some sense, I'm a little bit vague here. So deciding where to intersect the segments in the slab with the x coordinates, so locating the slab, is here done geometrically. So we may come back to this, how do we exactly do this? But roughly speaking, this will run in logarithmic in the number of edges. So if we have n edges, so our subdivision consisted of n edges, then we have at most 2n vertices. So that means 2n x coordinates in the sorted array. So the binary search there will be the 2 log of 2 times n, but 2 times n, the 2 before the 2 times n is just a constant. So every binary search then also for the y coordinates also takes log n operations. So 2 times log of n. Okay, but here is now the storage. So if you do this partitioning, what is now the storage cost? So here is a case where we are starting out with 11 edges. So we have 5 horizontal edges, and then we have 6 skew edges, up and down, up and down, up and down. So we start with 11 edges. If we are partitioning, we are adding many more edges. So you can see we are adding 6 slabs, and every slab has six edges. So 6 times 6 is 36. So this can be seen as quadratic, this example, because we have 11. 6 is 11 divided by 1.8. I give an example with 11, so you can make it more dramatic by taking more and more horizontal edges. So add one more horizontal edge, for example, then you have 12 edges to start with. You have 6 times 7 then in the number of slabs. So the number of slabs, the number of edges actually increases. So the storage cost, even though n times square of n is more likely, the storage cost will be quadratic. And that may be a big problem to store. If you start out with already um, large number of edges, say a million, then squaring that starts to be a million times a million, 10 to the power 12. So not really good to think about. Okay, so therefore we will now abandon this, not entirely this data structure, but we will refine it. So here is another exercise. Think again on the doubly connected edgeless representation. Um, and if you would store your subdivision, your partition as a doubly connected edge list representation, count exactly how many edges you would actually need. And compare with the original subdivision. So we have 11 edges. Compare with your doubly connected edge list representation working with these half edges. Every edge has a twin. Um, how many of such half edges do you actually need? Okay, here is the motivating example to introduce what we will call trapezoidal maps. So we were bothered by this example where we had 11 edges, but then ended up with 36 edges in the refinement. Substantial increase. So here is how we can do it better. Instead of having our vertical lines all the way go, so we do have still vertical lines that go all the way, the left and the right. So this will introduce many edges. But if we are from those middle edges, so you can see if we only go to the next edge above and the next edge below, we can save a lot. So here, what we are essentially saving is 3 times 5. So we actually save 15 edges. Instead of 36, we are arriving at 36 minus 15, we are arriving at 21. So we go from 11 to 21. So almost a 2n cost. So if we start with n, but we can also measure this differently. So the storage cost is um, linear because we have at most 2n vertices. So if you look at all the vertices, there can be at most 2n, and this actually gives us an upper bound on the number of edges that we can add, also 2n. The exercise 2, I said something about 21 edges that we add. Verify this. If you like, work again with the doubly connected edge list representation to arrive at a precise count on how many edges you would actually now need to store the above subdivision. Um, okay, trapezoidal maps. We make two assumptions. our first case was actually already not in degenerate position because it had a vertical edge. Later we will see how to deal with this. I mean, because vertical edges, they kind of overlap with these vertical lines that we are adding in the trapezoidal maps. So we assume that everything is bounded. That's not a bad assumption to make, especially if we have a city. We are bounded. Um, and also we actually have no vertical edges. That's probably the assumption that's you can come to by shifting your map in a random direction. So chances then that you have really, so in some sense, it would mean that you would have no straight road running north. And that's very unlikely, especially in American cities. But skew your map a little bit, and that's um, not such a bad assumption. But we will see later on how to deal with this. So here for this example, and that will be our running example, I have drawn the trapezoidal subdivision. So we add vertical lines through we add a bounding box first, and then we add vertical line segments through every vertex. We stop the vertical line segment at the next edge or at the uh, limits in the upper or the upper limits and the lower limits in the rectangular bounding box. So this is an example of a trapezoidal subdivision. And you can see where the name comes from. The faces, they are either trapezoidals, quadrilaterals. Some of them are actually also triangles. But in general, all the faces are actually trapezoids. A rectangle is also a special case of trapezoids. Okay, do you want the formal definition now? Well, the construction of a trapezoidal decomposition actually gives this, so in some sense, it's adding of the vertical extensions below and above. And you can see that this is an algorithm that runs linearly in the number of edges. And you could say that there is a double loop, but an edge has only two endpoints. So it's not a quadratic construction. It is at most executed two n times. So every edge has actually two endpoints. And you can see that some of the endpoints are shared. Um, so this algorithm runs in linear time in the number of edges. Also linear in the number of vertices. Okay, we will make more precise counts on the complexity of trapezoidal maps. Okay, here is our first lemma. What about the faces? So every face is actually a trapezoidal, except if it has only one vertical side. So that is an important geometrical property. So to prove this, we will show that every face is convex. So if you think about the corners of a face, then either it's a corner of a bounding box, and there the angle is 90 degrees, or it is an angle where you meet a where the vertical extension meets the edge. So the edges are actually, because it's in general position, they're not vertical. So you will never have an angle at a corner that is more than pi, or that pi or more. Well, therefore, every interior angle is less than pi. So no interior angle is larger than pi. And that was a criterion that we used to determine convexity. Okay, every face is now convex, and there are at most two vertical sides to it. We have at least one vertical side because there is this box. Okay. Um, the fact that every face, so the vertical sides is the left and the right. Um, you can say, when do you only have one vertical case? Well, you could have the case where the left or the right vertex is actually, we will see cases like that. But where the two skew sides are joined. So this is when you have no vertical face. So this is when, well, let me make some drawing here. What you could have, um, is that if I extend this here, you could have that this is, and this would be a trapezoidal map that has only one vertical face. Okay, I'm defacing this here because the point is that we cannot have cases like this. So if we would have two skew sides, either above or below, then actually we would have forgotten to draw this vertical extension. So we cannot have these inner vertices. So this concludes the lemma on the shapes of the faces in a trapezoidal subdivision. Trapezoidal maps have therefore interesting properties. So uh, let us let us describe the shapes. So that will be very useful to determine a specific data structure to store a trapezoidal shape. So every trapezoidal shape is determined by a top and a bottom edge, and it has a left and a right vertex. So these four attributes uniquely define the faces in a trapezoidal map: top, bottom, left, and right. This is an example. Um, let's count what are the possible cases. Well, in a trapezoidal map, for the left point, you can either have that the skew sides are joined. So we actually don't have a left vertical point. The left point can be on top. It can be at the bottom of the trapezoidal, or it can be in the middle of a vertical extension. The fifth case is when the left point is a vertex of the bounding box. Now you may wonder, you know what? Wait, uh, do we now don't we have two of the bounding box, a top or a bottom? Well, it suffices to take one of the two. You have to take the convention that either you take the top left or the top right of the bounding box. Okay, our third exercise is mirroring the pictures that I have here. So what are the possible cases for the right point? So you have a mirror and you reflect. So five possible cases. What about the storage cost? So we introduced the refined partitions. We started with slabs, and then we had a quadratic storage cost, or n times the square root of n. We actually have with trapezoidal maps a linear storage cost. So linear in the number of vertices, linear in the number of faces. Very advantageous. So how do we count the number of vertices? Well, we have the bounding box, so that's 4. Then we have the endpoint of the edges. We have n edges, and therefore we can have at most 2n um, vertices. And we also have the extra vertices that are at the end of a vertical extension. So that gives us 4n. So this gives a total count of 6n plus 4. Okay. Um, Now, if we want to number the trapezoid, we look at the cases for the left point. So the last statement of the lemma again. The lemma is proven, could almost fit it into one slide, but then I would lose the statement of the lemma. So we want to arrive at 3n plus 1, and we have 5 cases. So how do we get to the 3n now? Well, the left point is a corner. So if that is the case, then there is only one trapezoid. Or it is the left point of an edge. So that means we have n edges. So we could have n. Or um, the left point can be the left of at most two trapezoids. So that gives us 2n trapezoids. So this makes that we can arrive at 3n plus 1 trapezoids if we consider the cases for the left. If we, why don't we consider also the right? Well, then we would double count. So we don't double count. So it suffices every face of the trapezoidal map has a left point. So it's either a corner of the rectangular box, either a left point of an edge, or it is can be the left of at most two trapezoids. Okay, so that is an upper bound of 3n plus 1. Good question, are these bounds sharp? And I don't think they are sharp. Can you draw a trapezoidal map such that you exactly have 3n plus 1? Good question. Um, but for us, we are already very happy because we have a linear storage cost. Big improvement over our first partitioned subdivision into slabs. Okay, why did we, so now if we want to store this, we may want to store the adjacency information. So you can go from one trapezoid, one face to the adjacent ones. So how do we define adjacency? Well, here is an example. So adjacency means to the left or to the right. So the definition says that two trapezoids are adjacent, two faces of a trapezoidal map are adjacent if they meet along a vertical edge. So here for the delta, the trapezoid in the middle, we have two left neighbors and one right neighbor. So which actually, how many neighbors can you have? Because that is important as far as the data structure goes. So in the data structure, you want to store the top, the bottom edges, and also you want to store the left and the right vertex. You would also like to store now pointers to the adjacent trapezoids. Okay, so you have to be careful if you do this because it may be that you have to work with a list of pointers, not just, you could think of that there are at most two neighbors, either to the left or to the right. But here you see you have an example where we have many vertical edges. So the extension, the vertical extension created many vertical edges because we have vertices with the same x coordinate. And that creates, here you can see you have 5 left neighbors to this face in the trapezoidal map. So, not in general position means you have coordinates that are the same. Well, then we cannot say anything about the bound on the number of adjacent trapezoids. Otherwise, and here it now gets to storing trapezoidal subdivisions in general position? Well, you see now that there can be at most two neighbors. So don't have a proof for this, but you can use the argument, you can use the example of the previous slide as a contraposition argument. Suppose you would have more than two left neighbors. That can only happen if you have vertices that have the same x coordinate. So that is so if you have now in general position like this example here, then you can store every face by four attributes, two edges and two vertices, and then also the adjacency information. Um, So the edges, if you store them with a half edge representation, the edges actually also have incident faces. So in this way, you could climb up to the uh, via these half edge representations or storing the incident edges. You can actually use this, um, use the navigation through your trapezoidal map. Okay, so the last exercise is elaborating on the last paragraph of section 6.1 in our textbook. So here is the example again. Um, use this example to define the specialized data structure. It's good actually to write it out for the example, and you can explain how, and you can focus, for example, on the central face. If you can define it for the central face, then you could say that, hey, this trapezoidal map is actually a list of faces, and for every face you store the edges and you store the um, also the adjacency. If you would be using the doubly connected edge list, then if I may draw here again, so you would have these additional vertices. So you would have these additional vertices here, and that would work as well. But it's probably better to use the specialized data structure. So you could indicate also in your in a more elaborate solution to this exercise, you can make the comparison with the doubly connected edge list. If you would use a doubly connected edge list, you would end up with storing many more additional vertices that I started to sketch here. Uh, and it would not be so economical as a specialized data structure. All right. I'm at the end, and that is already after half an hour. So I was also economical with my presentation. But I still have to flash up the documentation for Sigal. So that is also one of the activities. So I hope that this pre-recording gives you some idea on how to start writing the exercises. That's the purpose of the exercise, is that you slow down a little bit. So in some sense, even if the pre-recording lasts far less than 50 minutes, going through this, pausing it, and thinking about the exercises may give you the full 50 minutes. The goal of the lectures are that you find your way in the textbook, also that you can get a handle on the exercises in the textbook. Okay, to finish off this pre-recording, let me move to the user manual of the 2D arrangement parts. The layout works fine, I see. So you can see there is the table of contents of this part. What you don't see are the 2D arrangements. But what you should see here is the point location queries. So the arrangements, we will later in this course actually see an entire chapter on arrangements. So it's somehow a little bit unfortunate that the Seagull Swig bindings don't really wrap this so explicitly because it's really a central part. So I'm going to click on the point location queries here, section 3.1 of the Seagull. So even if you're not a C++ programmer, from an algorithmic point of view, it's still very useful to actually browse through the documentation and to actually see where the notions come in. So there are several, so arrangement here means that you have arrangements of line segments. Oops, I'm scrolling too fast. But here you see that I should scroll like this. So if you have a point location strategies, there are point location strategies that do not use any additional data structure. Um, so there, but then you have the constraint triangulations that are here. Um, we will later in the course see much more about triangulations. Um, but the point is, and here the last chapter now, the last paragraph now, as mentioned above, and here as mentioned above in my slides. So the data structure needed and the trapezoidal map. So here the construction takes an n log n. So there is the sorting n log n that needs to happen anyway. Okay. Um, yeah, so the main point, um, I'm a little bit out of inspiration now. So it's mainly the word trapezoidal map that I want to highlight here. So the presentation of the lecture should give you some way on how to navigate a software package such as Seagull to actually realize that everything can be done very efficiently. Um, so this is a geometric problem. Know where you are on your map. Very, very practical. So knowing how to do this is good, but we have now technology, smartphones to do that. So I hope you can realize a little bit through this lecture why this can be done so efficiently. So in summary, what did we do? We have a query similar to the database terminologies of the previous chapter, but now we are constructing trapezoidal decompositions of a map, and that solves our point location problem.